Problem 8. An air puck is tied to a string and it revolves in a circle on a frictionless horizontal table. The other end of the string passes through a hole in the center of the table and a mass is tied to it. That suspended mass remains in equilibrium while the puck on the tabletop revolves. So let's start out by drawing a free body diagram for each of those two objects. This is a system of connected objects. So let's do a free body diagram for the hanging mass. It's experiencing gravity pulling it down. We're labeling its, that's M2. Labeling its mass as M2, and tension force is holding it up. So some of the forces in the y direction is 0 because that block is in equilibrium, it's stationary. And so we find that tension equals the weight, equals M2G. And here's a free body diagram for the puck on the table. This is kind of a side view. There's the vertical direction. That's pointing toward the center of the circle. The puck is going around like this. So there's the tension force pointing toward the center. There's the normal force. There's the weight, the gravity force on the puck. And we don't really need to worry about the y direction. There's no friction involved. That's not going to help us solve the problem. All we need is the radial direction, or centripetal direction, I guess, whatever you want to call it. And we've got tension force, and that equals mass times centripetal acceleration, and our sign conventions tell us we should put negative signs in front of both of those things. And this tension force, because there's a string connecting both objects, is the same as the tension force we found for the string holding up the hanging mass. So these two tensions are the same value. And that means we can solve for the speed of the puck with a little bit of algebra. RT over M square root. Okay, so problem 8, I like problem 8 because it combines several concepts. We're still doing a Newton's second law analysis like we've been doing for a lot of the semester, and we're doing it for a situation where there's centripetal motion involved, a centripetal force, and circular motion of the puck. And it's funny, this problem seems kind of complicated when you look at it at first. And the solution almost, I remember the first time I did it, the solution almost seemed too easy. But it's simple because we have the right tools for the job now. We understand that when there's string involved, the tension is the same everywhere. So we can find that tension force by analyzing one of the objects, and then that tension force is providing the centripetal force that holds this puck in its circular motion. Okay, that's it for problem 8.